Hello everyone, today we are going to derive the equation of continuity or the continuity equation or the equation of mass conservation, or you can also say conservation of mass. So let us consider a flow field. Within the flow field, let us consider a control volume. Here we are deriving it in a rectangular coordinate system. So we will take the control volume in the form of a cube. Let us consider a rectangular coordinate system that looks like this x, y and z components, and inside this we have the control volume, which is a cube of volume delta x, delta y and delta z. So the delta x, delta y and delta z are the elemental length here in the x, y and z components respectively. Now we will write this equation in terms of the velocity component, three velocity components for the 3xyz coordinate system. Here I am writing it in a vector form. For the velocity, xyz components and the final velocity vector is a function of x, y, z and t. So this is a three-dimensional unsteady state without any assumptions till now. Rho here is a function of x, y, z and t. That means it can be used for a compressible flow as well as incompressible flow. So let us write the equation for conservation of mass. So the left hand side we will have the common statement, that is rate of accumulation of mass in the control volume, and in the right hand side we will have rate of inflow of mass into the control volume, like how much mass is coming into the control volume, and we will subtract the rate of outflow of mass that is going out of the control volume, that is the rate of mass that is going out of the control volume. So that makes the statement of our conservation of mass. Let us number this as equation number 2. Now let us write this expression in terms of mathematical form. So left hand side could be dou t of rho delta x, delta y, delta z, that is mass. Let's call that equation number 3a. In the right hand side we will do little bit of surface wise here. So we will write this expression in terms of different surface. So let us draw the control volume here once again. So here is the control volume. As you can see, it's a cubical control volume. So let me first write down what I just told you. Let us do this the right hand side. Let us do this separately for each pair of surfaces. We have 3 pair of surfaces. Some mass is coming into certain surface and going out of certain surface. So first let us consider the surface which is normal to the x direction. So here it is normal or perpendicular to the x direction. So here is the surfaces which are perpendicular to the x direction. Let us highlight those, shall we? Yeah, so this is the surface and the left surface. These are the surfaces which are perpendicular to the x directions. And the velocity component perpendicular to that surface is Vx. So if you want to write down in the form of rho a and v, we will have rho delta y delta z Vx at x minus rho delta y delta z Vx at x plus delta x. That's mass entering into the control volume minus mass exiting out of the control volume via the surface which is normal to x direction. Now for the other surface, the surfaces which are perpendicular to the y direction. Let us have a look at this one from the figure. That will be the surface, the top surface and the bottom surface, as you can see here. And the corresponding velocity component is Vy, and we can write that inflow as rho multiplied by delta x multiplied by delta z at Vy at y minus rho delta x delta z Vy at y plus delta y. Let's number this equation as equation number 3c. Now exactly in the same way we can also consider the surfaces that are perpendicular to the z direction here. And here we will get rho multiplied by delta x delta y at multiplied by vz at z minus rho delta x delta y vz at z plus delta z, equation number 3d. Okay, after this we can combine all these equations we have just written and we can get the overall or the generalized mass balance equation. 3a equals to 3b plus 3c plus 3d, and this gives us dou dot t of rho multiplied by delta x delta y delta z is equals to, we can take equation number 3b 3c and 3d, which will give us rho multiplied by delta y delta z multiplied by vx at x minus rho multiplied by delta y delta z vx at x plus delta x plus rho multiplied by delta x delta z multiplied by vy at y minus rho multiplied by delta x delta z multiplied by vy y plus delta y plus rho multiplied by delta x delta y vz at z minus rho multiplied by delta x delta y vz at z plus delta z. Let us number this equation as equation number 4. Now, as we always do, let's divide equation number 4 by delta x delta y delta z. Now the equation will become dou dot t of rho, that's the left hand side, that we can write dou dot t equals to rho vx at x minus rho vx at x plus delta x divided by delta x plus rho vy at y minus rho vy at y plus delta y divided by delta y, and then plus we have rho vz z minus rho vz at z plus delta z divided by delta z. This equation number 5. Now we can take limit delta x tends to 0, delta y tends to 0, and delta z tends to 0. And if we take that, we know that we will get the expression in terms of the differential form. Let us see what it will be. Left hand side will remain as it is, that is dou rho dou t, and in the right hand side we will have minus dou x of rho vx plus dou y of rho vy plus dou z of rho vz. Let's number this equation as equation number 6. Now, if you know about vector form, we can also write this expression in terms of vector form. Before that, let me just write down here that this is the equation of continuity, as you can see from x, y and z for the Cartesian coordinate system. Let us try to write this equation in terms of coordinate independent form. Let us generalize this equation in terms of vector form. That will give us dou rho dot t equals to minus del dot rho v. If you look at that, that's equation number 7. Now in this equation, del dot rho v, let us see what is this del, and that v we already have before means. So v, as you know, is ex vx plus ey vy plus ez vz. Del is ex dot o x plus ey dot o y plus ez d dz, which is the differential operator in the x, y, z coordinate system. That's the Cartesian coordinate system. If you want to write in terms of r theta z, you can also write. There's a very special and interesting derivation of this expression. If you want, I can make a lecture for this, the cylindrical and spherical coordinate system. Do let me know in the comments if you want that. I'll be very happy to make a lecture for that. Now these are del and v, and this equation, as you can see here, is independent of any coordinate. You can write it for any coordinate system if you want. If you know the v and del for any coordinate system, you can write it using any other coordinate system other than the Cartesian one. Now if you want to take the second term and divide it into two parts, we can get this expression like this. This is a property of vector dot product. If you want, I can go through that in some other lecture. If you combine the first term and the third term in the left hand side, that is dou rho dou t plus v dot del rho, then we will get a very special and interesting term. If you know it, is written in terms of capital D, which is called the substantial derivative, and this is our expression of continuity equation, the generalized form in terms of the substantial derivative. Thanks for your attention. I hope you understood equation of continuity. Bye bye.